the Z-test. The Z-test is a really uncommon inferential statistic in psychology. You don't see it very often. But having said that, it is, believe me or not, a relatively easy introduction into harder stats. So, our assignment this week only has 3 questions, so they're probably hard. Okay, let's say that I know that scores on an anxiety inventory are distributed normally in the population with mu is 8 and sigma is 3. We immediately make a grocery list. I'm just looking where I am in the camera. Okay, we immediately make a grocery list. Mu is 8. Sigma is 3. Whatever number I see, I write down, so I can make use of it, with the right symbols so I can find them back. Okay, so some sort of anxiety questionnaire population. Okay, the higher someone's score in this anxiety inventory, the more anxious they are. Okay, so bigger number means more anxiety. Okay, got that. I expect that anxiety in RDP student population during the final examination period is higher than it is in the general population. Okay, well, in the population, I know that this is the mean anxiety score. So I already know I'm looking for something higher than 8. Okay, I can do that. I ask 25 students, okay, immediately add to the grocery list, n equals 25, that was my sample size, to complete the anxiety inventory during their exam period, and I found a mean anxiety score of 11. Okay, this has yielded 11, x bar. I now have the population mean and a sample mean. I like to do this with the arrow. Whatever you do, I don't care. Write it down though. Find a method that works for you. This works for me. Population mean, sigma, the standard deviation, and out of my sample, I drew that mean. I got that mean. Okay. All right. Formulate symbolic, null, and alternative hypotheses for this study. I'm just going to zoom in a little bit so it's a bit easier for me to read as I stand here, because my device is quite far away. Okay, well, I expect that anxiety in students during that exam period is going to be higher than the population. Is that directional or is that a non-directional hypothesis? Directional, of course, direction. Higher than, that's a direction. Okay, so H0, H1, mu1, mu1, mu2, mu2. I expect that in the alternative hypothesis, there's a bigger difference. So that was a terrible sentence. So I expect my alternative hypothesis to be RDP students more anxious than population. RDP more anxious than the population. And then the null hypothesis has to be the opposite of that, smaller than or equal to. Remember the equal to, the difference could be 0. And then the null hypothesis is supported by empirical evidence. Okay, well, that was easy. Question 1 done. Okay, what else can we do? I know what's coming. I bet you there's a Z-test. Question 2. Conduct a Z-test. To test. Great structure. The hypothesis proposed in question 1. Use alpha is 0.05. Okay. Are the results significant? Report the results in APA style. Okay, here I want to take just a tiny second just to make sure that we fully understand why we're doing a Z-test. You remember the Z score. I could convert, this mean, into a Z score if this was not a mean but an observation. So what I'm saying then is, imagine that your anxiety score was 11. Well, then I can compute a Z score. Z equals 11 minus mu divided by 3. And then I can look at a standard normal distribution. Of course, standard normal distribution. Mean of 0. This is going to be what? 8, 11, that's 3. Is it 3? Yeah, 3. Okay, this is wonderfully done. 3 over 3 is 1. Okay, so what do I know? I immediately know your, let's do that in a different color, that's reality. Your anxiety score of not 2 bars that way, of 11 is 1 standard deviation over the population's anxiety score of 8. But you must agree with me, I'm now trying to do something completely different. This 11 is not the score of one person. I tested 25 people, gave them the anxiety questionnaire, and on average, their score was 11. So I am not trying to position one score into a distribution of other Z scores. Now, I drew a sample, which has a mean, and I'm trying to figure out where that sample mean is in a distribution of sample means. It would be idiotic to see where a sample mean is in a distribution of individual observations. That is the infamous apples and pears. These are 2 completely different things. I can't compare them. But with a Z-test, not a Z-score, but a Z-test, I do something different. I do what I just said. I see where my sample mean is in the whole distribution of other sample means. And then I can see where that mean is relative to the population mean. After all, if I erect a sampling distribution of the mean, right? I take a population, let's say all RDP students, and I keep testing them again and again and again. I draw a sample and another sample, all of the same size. Every time I draw the samples and I give them that anxiety questionnaire, I compute the mean anxiety score in that questionnaire, and then I count how often each mean anxiety score occurred. Then what I'm erecting is a sampling distribution of the mean. And that sampling distribution of the mean, because in that theoretical distribution, I have incorporated every possible RDP student, the mean of the sampling distribution of the mean, sorry, that's just what the thing is called to make it easy. I'll call it the SDM again. You can also call it the sampling distribution. The mean of the sampling distribution of the mean equals the population mean. And that makes sense because, like I said, the sampling distribution of the mean contains samples of every possible RDP student, taken again and again and again until every possible combination of students has been tested. This I can avail myself of. Think of the logic, it's beautiful. If I now want to see where my sample mean lies, I need to convert it to a special form of the Z-score, which is captured in this particular this particular sampling distribution, and then I can see where my sample lies. Now imagine that my sample mean, converted to that special Z-score that we will get to, lies here in the tail of the distribution. That's very far away from the mean of the sampling distribution, which is the same as the mean of the population. So then I can say, okay, well, my RDP mean is very far removed from the mean of the population. So far removed that I can say if only 5% of all the sample means in that sampling distribution are this big or bigger, that's not a coincidence. That's such a small percentage of observations, something real is going on. And of course, that something could be all sorts of things, but in this case, I've hypothesized it has something to do with stress because of the examination period. And that's how a Z-test works. Beautiful system. Now, to do all this, I need to avail myself of a formula. And that formula, you have to agree with me, is going to look quite a lot like the formula for a Z-score. This is what we will be using. Z, this is not a Z-score, but a Z-test, okay, equals my sample mean, I already have that, minus my population mean, well, I already have that too. And in this case, we use some special symbolism. We say, okay, population mean, but remember, I just showed you that's the same as the mean of the sampling distribution of the mean. Okay. Well, I have this thing though. This is the same as that. Mean of the sampling distribution of the mean is the same as the mean of the population. So I already have this, I already have that. And there's only one more term, and that is the standard error of the mean. Okay, that one I don't have. But of the 3 terms I need in this formula, I already have 2. 2/3. I don't even have to compute. They're given to me. This is one of the few tests that you can run without seeing the data. As long as someone gives you the proper means, you can compute the test. In a lot of stats, that's not possible. Okay, so I need this thing. The standard deviation of the sampling distribution of the mean, because that's where I'm placing my sample mean. I want to see where it is. Okay, well, the standard deviation of the sampling distribution of the mean has a special name, the standard error of the mean. And that thing is computed as sigma from the population, standard deviation from the population, which I already have, divided by the square root of big N, which I already have. You have to agree with me. This is not as terrifying as it looks. These 4 numbers have given me almost everything I need. Okay, I can compute that. This is 3 divided by the square root of 25, and that's going to be 3/5. In it. Okay, well, I can compute that. That's 0.6. Okay, I'm willing to believe that. 0.6. Then what? Well, I have this. I just need to complete the formula. My special Z score, which we name the Z test, X bar. Okay, that's my sample mean. I have it right there. Minus the mean of the sampling distribution of the mean. This is the same as the population mean. Right there. Okay. Divided by the standard error of the mean. I just computed it. 0.6. Okay. And if I quickly look at my notes here, 5. Mental note, 5. I'm going to put that up here. I know this gets a little messy. You can do this a little bit more organized, but I'm just kind of trying to keep a little bit of track of things. My special Z is 5. Okay. Almost there. I now need to make a decision. And that decision is in my sampling distribution of the mean, which has a mean, which is basically where we have converted this to special Z score, so that is now a 0. That represents population mean. We just know this. This represented, and I use red for that, so let's be consistent. A population mean. No longer the number 8. This also gets converted. It's now 0. We don't have to worry about this. If you find it a little confusing, don't be confused. This is the mean of the population. Okay, we're looking at a sampling distribution of the mean. My question now is my 5, which is very far out in the tail, think about it, 5, very far out in the tail, 1 standard deviation, 2, 3, 4, 5, all the way 5, way back, is that among the 5% most extreme values? Well, how do I know? Well, that means I need to find another special Z value, and this, remember, this mu, that was 11, this 5 here, this really represents my 11 in the real world. I'm sorry, this was the 8. That's the population mean. This is my sample mean. Okay. Now, how do I know if this 5 is in the 5% most extreme values? You could also do 1% most extreme values. By convention, we use 1 or 5. Let's stick with 5 because it was given to you. Alpha is 0.05. How do I know? Well, that's actually really simple. All I need to do is find that special value of Z that marks 0.05, a proportion of 0.05, 5% of the most extreme cases. Well, for that I need my textbook. If you do this a couple times, you'll remember the Z value. I know it's 1.65, but I'm just going to go through this with you. I look at my textbook. Okay. Well, let's have a look here. So I need an area beyond Z with a proportion of 0.05. Well, let me have a look. Let me do some random sampling. For a Z value of 0.4, area at or above Z is 0.34. Yeah, that's 34%. That's way too big. That's too much. If my value is in that, it's a very common value. It's not extreme. It's likely to have occurred by chance. I obtained that by chance, that it's just bigger than the population mean. No, I don't want that. Let's continue. Let's keep going. I'm just doing another one. 1.70. There, the area beyond Z is 0.0446. Okay, I'm getting closer to the 0.05 that I want. Okay, well, if I go to 1.65, I find area beyond Z is marked by, the area beyond Z, the proportion under the curve here, so area at or above Z equals 0.0495. Okay, I think that's a good Z value. Now, some students might say, yeah, but if I look at the value above it, Z is 1.64, I get 0.0505 for that area beyond Z. Yeah, but that rounds to 0.051, that is 5.1%. I would recommend rather be a bit conservative with these things than be a bit too liberal, because then you may make a wrong decision. You may be too liberal in the decision you make. So, for this area under the curve, area at or above Z, 0.0495, that rounds to 5%. I find a Z value of 1.65. Okay, 1.65. Let's see, I'll put that in. 1.65. Are my results significant? Yes, most certainly, because 5 is more extreme, bigger than 1.65. I like to use the term more extreme because you could also have a non-directional hypothesis. You might look here, and strictly speaking, if it would have been minus 5, that's also more extreme than minus 1.65, right? But not bigger than, because it's a more negative number. That's why I like that more extreme. Now, strictly speaking, had that happened, had I found minus 5 for this mean, there are statisticians who say then you are not allowed to call that significant because you had a directional hypothesis. You predicted something in this direction. If you find something in the opposite direction, too bad. You should have formulated a better hypothesis. And because of that, there are statisticians who say it were better to never do a directional hypothesis, only do non-directional. If you want to learn more about that, you've got to take advanced stats with me. Okay, so we have all this. Now I need to put this into something that resembles APA style. We've decided that this is indeed significant. Well, then I do Z, and that Z would have to be in italics, but I can't write that, so I just underline it, but should be italicized. That is APA style. And that Z equals 5, comma, not a semicolon, not and, not a colon, comma, P also in italics, still can't do that, smaller than 0.05. And you will find that SPSS gives you a precise number, because SPSS can do something that you and I cannot, because SPSS is a computer. SPSS can compute exactly what proportion of values is 5 or larger. So SPSS here, this number is made up, don't quote me on this. SPSS may give you something like 0.0, this is pretty extreme, so let's say 0.0035. And in that case, if you have that exact value, then in APA style you would say P equals 0.0035. But when you use a table, you don't know what the exact P value is, so you stick to P is smaller than 0.05. Let's not do it in red. P is smaller than 0.05. Okay, Z test. Hey, survived. It wasn't that bad, I think. Maybe your mileage varies. Now, let's look at the final question. I'm just scrolling there. I hope all this makes sense, and I hope that the little bit of additional explanation of sampling distribution, how that relates to z-scores, position of an individual in a distribution of z-scores, z-test, position of a sample mean in a distribution of sample means. I hope that makes sense. Okay, final question. Imagine I happen to have sampled particularly anxious students and the actual mean anxiety level is lower than the value I found. This means I have falsely rejected the null hypothesis. What kind of error have I committed, type 1 or type 2, and why? So this would be error, measurement error. You have introduced something by drawing a biased sample. Highly anxious students are supposed to score highly on an anxiety questionnaire. They're anxious, right? So that is a type of bias. That is not a random sample. If you draw a random sample, you may get a couple of students that are above average in anxiety, but you'll also get some that are below average in anxiety, and that will level out very nicely. So in this case, what have I done? Draw it out. I have rejected the null. So the real state of the world is the null should have been accepted, supported. In real life, people say null hypothesis is true. That's really ugly. The hypothesis is not true. It is supported or it is not supported. That doesn't mean it's true. There could be all sorts of things going on. Or I have the null hypothesis not supported. And this is reality. But then I have said sorry, this is hideous writing, except H0. What have I done here? Okay, it sounds to me like, if we're looking at this question, I have rejected the null. This is decision. I really should not try to write sideways, but decision. I rejected the null, but in reality it was true. Type 1 error. I could have done the opposite. I could have accepted the null, well in reality it's not supported. So in reality there is a difference between the anxiety score in my sample and the population. But I have said, no, there is no such difference. That is a type 2 error. Now, if I reject the null, while in reality the data do not support the null hypothesis, so in other words, there is a difference, and I say there is a difference, I was right. This is a correct rejection. And if I do this, I accept the null, I say there is no difference, and in reality there is no difference, I've made a correct acceptance. I should indeed accept the null. So in our case, I had too many anxious students in my sample, I missampled, this can happen, right? That introduced bias, and as a result, I falsely rejected the null. That's a type 1 error. Thus, and thus alone, you approach this scenario. I hope this was useful. I hope this clarified things. Let me know if it was helpful. If you have any questions or have spotted errors that almost invariably creep in, let me know. See you soon.